Okay, we've had a few videos where we've been looking at NMR to work out work out the structure of different compounds. Now, just have a little break from that to talk a little bit more about what causes chemical shift. So, okay, so here's our ppm scale here, and I've written it down here going from 0 up to 12. And if you remember from near the beginning, I said what we're actually doing as we go along here is increasing the magnetic field strength, okay? The applied magnetic field, right? So if we have, we've got a peak here, which is about 1. I'll just draw it as a singlet. Yeah, that would be typical for any hydrogens which are on a carbon, which is a long way from electronegative elements. Okay. Now, what that means is, in order for these hydrogens to absorb, the radio waves, you need to have quite a strong magnetic field. Okay. And the reason why you need a strong magnetic field is because these protons are said to be shielded, highly shielded. Okay. Okay, they're highly shielded. That means there's a high electron density around them. And those electrons block out the external magnetic field. So you need a stronger magnetic field, external field, in order to make them absorb the radio waves, because all these electrons are high electron density, that's blocking out the external magnetic field. Okay, so here we've got our highly shielded protons, if you like. All right. Whereas if you think down here, now here, these are said to be de-shielded. They're de-shielded. That means there's low electron density. There's low electron density because those protons are near to electronegative elements, and those electronegative elements are withdrawing the electrons away from them. So because there's low electron density, you don't need such a strong magnetic field in order to make them absorb radio waves. Okay, so the most de-shielded protons that are you can get about 12. Okay, about 12 ppm. I mentioned once before that is actually due to a carboxylic acid proton. Okay, so you've got 2 electronegative oxygens there in the vicinity, removing electrons from this hydrogen. That makes it very highly de-shielded. Okay, that doesn't come up in problems so much. One of the most common ones that comes up, we've seen it a lot, haven't we, is this one, about ppm of about 4. Okay, and that is when you get protons which are attached to a carbon which itself is attached to an oxygen. So that oxygen could be be part of an ester, or it could be part of an ether, or it could be an alcohol. Okay, so but whenever you have these hydrogens attached to a carbon which is directly attached to an oxygen, that's typically about 4. And the other one, which I always remember and comes up an awful lot, is when you have a ppm of about 2. And this is characteristic of when you have protons which are like that, which are next door, not to an oxygen, but to a carbonyl group. Okay, so these protons here, these were going to give you a ppm of about 2. There, you know, when you get your in the exam, you get your periodic table and you get a data sheet, and it's got the ppm of lots of different protons. But these are the ones I'd really remember. I'd remember that when it's not near anything, it's about 1. When it's next door to a carbonyl, it's 2. When it's next door to an oxygen, it's about 4. Also quite useful to remember, if you have 2 equivalent, so say I've got CH3 there, imagine if I had a CH2, which is a long way, they tend to be just a little bit higher, tiny bit higher than a CH3. And likewise, if you had a a carbon with just 1 hydrogen, that'd be a tiny bit higher still, but so that makes a small difference. Right, time now to talk about this 0 ppm value. Right, now the whenever an NMR spectra is carried out on a compound, they always add, so I'll draw this in here, there was what is in the spectrum but isn't actually marked is there'll be a signal which is on 0 exactly, okay? And that is due to the reference compound. Okay, now the reference compound is tetramethylsilane, which looks like this. Right, so you have silicon, CH3, okay, CH3, so 4 methyl groups. Okay, this is tetramethylsilane. And a drop of this is always added to the sample. And that's to set the value at 0, if you like. That's like an internal benchmark, right? So you define that as being 0. And then if you get a signal at, say, 4 ppm, okay, what would that mean was in order for that, the strength of the magnetic field there is 4 parts per million weaker than it is here. Okay, so this is like an internal benchmarking thing. You put your tetramethylsilane in there, and that's defined as 0 ppm. That requires, tetramethylsilane requires the biggest magnetic field in order for it to absorb the radio waves. And you compare everything to that. Now, why do they use tetramethylsilane as a reference compound? Why do they use that? And this is a very common question in an exam for 2 or 3 marks. So let's have a look at that. So why tetramethylsilane as reference? Well, firstly, the TMS protons are more highly shielded. Than any others. Okay, so that means the reference peak, the TMS peak, which is usually not shown in the spectrum, is well away from all the other peaks that are in your spectrum. So if you had your reference peak in the middle of your spectrum, that would make matters confusing. You wouldn't know which one was which. So that's why it's well away from everything else. 2, TMS is very unreactive, so it's not going to react with the sample and mess it up, and so you don't know what what was the original sample and what the reaction products. And 3, you can probably tell by looking at this structure. If you look at this here, right, what's that going to give you? It's going to give you 1 peak with no splitting. Which is also, you don't want it if you had multiple peaks all over the place. It would make the rest of the spectrum very confusing. So those are the three reasons why we use TMS as the reference compound. Why do we need the reference compound? Well, it's almost like saying, right, this is sea level, if you like, right? This is right 0, and we compare the magnetic field strength, so all the other peaks, to that one. So like I said, this one here, you would this very high ppm, this would require magnetic field strength of 12 millionths weaker than the magnetic field strength you needed for the TMS. Okay, before we finish this video, I just want to talk about splitting a little bit. I don't want to say what causes splitting, but I just want to talk about it. Now you've probably noticed when I'm drawing these spectra that right, so I'll draw they always look symmetrical. So that would be a singlet, looks like that. A doublet, they would be the same height. In a triplet, you always get one. That middle one is double the height of these two other ones at the side. In a quartet, then you get two in the middle, which is the same height, and these two are like that. And if you go up to a quintet, then you get the same sort of symmetrical pattern. So there's obviously a reason for that, which we won't talk into. We'll talk about the moment. We will talk about it later. They don't really ask questions on it, but it's quite easy to understand, and we will talk about that later. And there's a quartet, and that's a quintet, and so on. So just in case you're wondering why I'm always drawing them to be symmetrical, is because they do actually look symmetrical. And as I say, we'll talk about the reasons for that later.